So in chapter 10, we had started alluding, and especially in that last practice exercise, we had started alluding to some of the things that determine solutions. And so solutions, of course, are a mixture of two substances, which we term the solvent and the solute. The solvent is what does the dissolving, often identified in solutions as the one available in larger quantity. While the solute is what gets dissolved. And so usually it's the one that's present in a smaller quantity. Now, there's a lot of factors that go into how solutions are made and whether or not they even form at all. But some other terms that we should be familiar with in this section. We've previously discussed these terms, but they are pretty important here, so we'll bring them back, which are homogeneous and heterogeneous. So a homogeneous solution is visually uniform. It's what we might see if we mix salt and water together. So if you mix salt and water, the salt will dissolve in the water, which makes the salt the solute and the water the solvent. But once all the salt dissolves, we can no longer see any of the salt. So the mixture is completely uniform. And so we would say that that is homogeneous. Heterogeneous is not visually uniform. It may have different regions of different composition. And so we often use the term soluble and insoluble, meaning whether or not a solvent and solute pair are able to mix. But we also sometimes use these terms miscible and immiscible. Now these are similar terms, but they have to do primarily with liquids. So miscible are two liquids that are soluble with each other, whereas immiscible refers to two insoluble liquids. Now, except for the case of gases, which we really won't cover here, gases have very, very different properties when it comes to solubility. What determines whether things are soluble? Solubility is determined solely on the basis of intermolecular forces and specifically how polar molecules are. So we could talk about salt, and we could also talk about naphthalene. Naphthalene is an organic molecule. It's a hydrocarbon. Made up of 10 carbons and 8 hydrogens. So sodium chloride, we know as an ionic compound, is very polar. Naphthalene, on the other hand, is a hydrocarbon. contains only hydrogen and carbon, and like pretty much any hydrocarbon, is highly nonpolar. So what if we try and dissolve these? Well, we could look at two different solvents. We can look at water. Water we know is a polar solvent. And we could look at hexane. Hexane is C6H14. Again, it's a hydrocarbon, and therefore highly nonpolar. So what do you think will be soluble with what? Do you think sodium chloride will be soluble in the water? What about in the hexane? How about the naphthalene? Do you think that'll be soluble in water or hexane? Well, the water, being a polar molecule, will be highly soluble with sodium chloride. But when the sodium chloride gets added to hexane, which is completely nonpolar, it will not be soluble at all. The opposite will be true for naphthalene. Naphthalene, which is nonpolar, we would expect it to be highly soluble in the nonpolar solvent hexane, but if we add naphthalene to water, we would expect it to be not soluble, just like the sodium chloride was with the hexane. So overall, we say molecules of similar polarity, doesn't have to be identical, but similar polarity, will tend to be soluble. And the reason that this has to be is in order for something to be soluble, we have to have what's called solvation take place. So solvation is an interaction between the solvent and solute molecules. Sometimes we refer to this as hydration, but hydration is just another term for solvation when we're using water. So what has to happen, and why water can dissolve sodium chloride but hexane can't, is we start with all of our water molecules, and then we start with all of our sodium chloride molecules, and they start out separate. And so the solvent and solute need to have some sort of interaction that's going to encourage the solute molecules to sort of break away from each other. And so we saw in the last chapter that the sodium ion, for example, can be attracted to the negative end of the water's dipole, the oxygen, and the opposite for the chlorine ion. The negative chlorine ion is attracted to the positive end of the dipole. And so that allows the sodium ion to be soluble in water. But if you tried adding sodium chloride to hexane, hexane's not polar, and there's nothing in hexane that can attract away the sodium and chloride ions, and so they choose to stay together, and it doesn't dissolve. And so we can also think that this is how soap works. So why is it that if you have something greasy on your hands, that if you run them under water, the grease doesn't go away? But yet if you use soap, both the soap and the grease are able to be washed away. Well, most grease, anything we would think of in that category, is nonpolar. And that, therefore, isn't attracted to the water molecules. But what does a soap molecule look like? So most soaps are long chains of carbons with this oxygen, this charged end at the end. We can easily make soap, something you can do at home. All you need is a source of these long carbon chains. These long carbon chains are fatty acids. So if you get a triglyceride, you can do this as simply as getting some Crisco. And then if you add sodium hydroxide to it, which is something you can easily get, you find that sold as lye, it'll cause the triglyceride to break apart and you make soap. Well, what happens with soap is that you have this long hydrocarbon chain. This entire section is nonpolar. And so what this nonpolar end of the molecule does is it attracts all of the oils off of your hands. But then what happens on top of that is then all these oils and all these nonpolar ends, which we can designate by these squiggly lines, sort of come together and form this spherical type arrangement. On the outside of the sphere is the ionic part of the molecule. And so now water comes along, and the water doesn't see any of the nonpolar part. It only sees this very polar section. And so when water sees this polar section, it takes the whole thing, which is known as a micelle, and it's able to wash the whole thing away. And so that's why we end up in a situation where water is able to wash away the soap and the grease, but without the soap, it's not able to do anything.